Okay, yeah, thanks, Shiva. Welcome, everyone. So the way we are going to do it, Rajat and I discussed. Oh, by the way, I should mention that it's my name and Rajat's name there. Neither of us is giving the talk. The talk is going to be given by Elena. So the way we are going to do it is that, so because our group has met a few times and we think that we have made good progress, so we will have the group members give the 3 talks divided among themselves. But I'll just start off by describing a little bit of what we are doing and why it is interesting, perhaps. So as you all know, that networks are very important because they are modeling real-life phenomenon. And one of the important things to study on networks are behavior of interacting particle systems, where the particles live on the nodes of the network. So people have been studying this for quite some time. You have seen this in many different forms, like epidemic models, opinion dynamics, information cascades, all sorts of things that are useful to study on a general network. So people started realizing maybe about 20 years ago or so that to better model real world phenomenon, you should allow for the fact that the network can also change with time as the process evolves. And the interesting thing here would be to consider a two-way feedback, as in the process at any given time, the evolution of the process depends on the underlying network, but the links of the network, they also evolve depending on how, what are the states of different nodes at a given time. So there is a two-way feedback, and these type of networks are typically called co-evolutionary network. This is also, although you can see that this is quite interesting, but unfortunately there hasn't been that much rigorous mathematical study in these models. So except for one case which have become quite popular in the last few years. So Duret made it popular in 2012 when he wrote a PNAS paper. So this is where the dynamics or the interacting particle system is the classical voter model. Elena will explain it in much more detail. And the evolution of the network is a standard rewiring type of evolution. And we want to understand how they jointly evolve together. So this is sometimes referred to as evolving voter model or voter model on a dynamic random network. So we want to understand this general area of co-evolutionary network. And this seems to be the only example so far where we understand, okay, maybe there is some work on contact process also recently, but this is one of the more well-studied example where we can try to understand how the evolution of the network and the evolution of the process on the network interact with one another. So this is what I mean. We are exploring some questions along these lines. Elena will explain more. So I think I'll hand over to Elena.
So thanks for the introduction. I hope you can hear me. Please feel free to interrupt me if you have questions or just comments. So as Professor Basu was saying, one of the main tools of our project is the fact that we are working with a dynamic environment. So we want to define a model in which the network will evolve in time. And how can we do this? Let's see. Let's start with an introduction. So our main goal is to understand, how can I point? Maybe like, okay. To understand and to reproduce maybe the results of this article here of Basu slide. In this article, there are the proof of a conjecture presented before by Duret and others. And in particular, I take this picture from that article. And in these settings, there is a conjecture for the sparse regimes. But what we want to do is to work in a dense regime. So even in this article, authors work in a dense, proposing the network in the starting condition as an Erdos-Renyi with the edge probability 1/2. The thing that we want to do is exactly the same, but we do not want to work with an Erdos-Renyi, but we want to work with an exponential random graph. And in order to find the same results, we also want to understand how we can propose this model to be in some sense near the classic case of Erdos-Renyi in order to find similar results. So, as Professor Basu was saying, as you can imagine, that could be different ways we can insert dynamicity in network. In fact, there could be different ways in which we define the way the networks evolve with time. And one can, for example, say, okay, during time, edges may appear or disappear. Or one can say, if I am a vertex, I can break my friendship with you and I can create another friendship. So the way I can create another friendship may change. We also may change the shape of the network, the random graph that we are using to propose the initial condition in some sense. So as you can imagine, there could be different models, approaches, and point of views. And as you can see, this is quite a hot topic in literature. And if you read the name of the authors, they are here or they will be here next week or tomorrow maybe. So if you're interested, this could be a good opportunity for you to ask them questions too regarding similar models. But now in particular, we will define specifically the model present here. So let's begin with the idea of the model definition. So we want to present a voter model dynamics. So we work with an opinion dynamics. To describe an opinion dynamics, we need a Markov process. In these settings, we work with discrete time. And so we have a Markov chain. To define this Markov chain, we need a state space. We will work with this state space. We have n vertices, and each of these vertices carries a binary opinion, say 0, 1, or red, blue, as you prefer. And in particular, there are m edges. These m edges are labeled, and each of these edges is assigned to a bond. What is a bond is a pair of vertices. So this means that we want to assign to each edge a position to link two vertices in some sense. So we admit also a multigraph. The particular thing is we start with a simple graph, but during the evolutions, as t grows, we can arrive in a situation like this, for example, where here there is a multi-edge, for example. And it makes sense because if you think to, I don't know, friendship networks, to have a multi-edge could mean, for example, that our friendship is very strong or something like that. The only thing that we do not admit is the creation of self-loops. They are not admitted. So later we will talk how to start our process, but now we want to define the way we perform a step. So how can we pass from time t to time t plus 1? So let's give a very simple intuition. Let this be the state of the Markov chain at time t, for example. We have several steps. So step 1, we choose uniformly at random a disagreeing edge. What is a disagreeing edge? A disagreeing edge is an edge that connects different opinion vertices, like this, that connects a red with a yellow. So I, for example, take this, I could take this or the other. So I start taking a disagreeing edges. Then, number 2, I choose the root of the disagreeing edges. I can pick this or this, with probability 1.5. Then there is something particular in the step 3. Anyway, because that could be 2 different scenarios, okay? Just think, in step 3, I read a random variable that is a Bernoulli with parameter gamma over n. If this random variable is 1, I will perform a voter model step. Otherwise, I will perform a reweighting step. So we have this parameter, say gamma, for example, that one can call voter model parameter or reweighting parameter as you prefer, that we want to play with, okay? We want to understand how the model changes its properties as we change gamma, for example. Just think of it. If gamma is exactly 0, the case 3b will be present in each step. If gamma instead is very, very big, we expect this phenomenon to be maybe more predominant. And so we will later learn how to play with parameter gamma. So let's now understand what does do avoider model step mean? So case 3a. In this case, the root assumes the opposite opinion. So for example, this red became yellow, and this is the final state. We are able to perform that step. So if we perform a voter model step, only the opinion can change. The network remains the same. There is not an evolution of the network, but there is an evolution, a change in one opinion. On the opposite side, on the opposite side, we perform the rewiring step. So we remove the edges and we move it in another position. To choose the other position, we pick uniformly at random another vertex, say the green, that can be every vertex but the root. So in this example, I move this edge from this position to this position. So the edges never disappear, they are always moved. Here can happen different things. For example, it can happen that I picked a yellow vertex, okay? So from a disagreeing edges, I end to a disagreeing edges as well. And in this model, it is permitted. This model is called rewiring to random for this reason. There are other versions of this model that are named, for example, rewiring to same, in which we do not permit these things. And obviously, we expect maybe the process to behave differently in terms of timing. And it can also happen that I pick a vertex that is already my friend. And in that case, I reinforce our friendship, creating a multi-edge. Obviously, the thing that cannot happen is that I create a self-loop. So I never will end in a self-loop situation. So this is how our model evolves. During the rewiring steps, what happens? Opinion does not change, it only changes the network. Okay, rewiring means we change the network shape. Voter model means we prefer to change opinions. Okay, so in particular, we know that we are working with Markov chain in a state space that is finite. So we expect it to, in some sense, converge to an absorbing state. So to look for the absorbing state is like asking, okay, what the process looks like at the end, okay? What is a possible final for this process, where there are no more disagreeing edges. So if you think to the classical voter model dynamics, the only final could be consensus. So with no rewiring, we only end in a situation where all the vertices carry the same opinion. Okay? There is not a minority that survives. But here something different can happen. And why? Because thanks to the rewiring, we can separate opinions, create different communities, if you want, different communities. And each of these connected components can also hold a different opinion. And so it becomes very differently and very interesting because obviously we can ask many other questions. For example, how can we describe the minority opinion? Is it able to survive? Is it able to conserve in some sense? And this will be one of our main questions. So now, instead, we want to discuss on how we want to start our process. So in the original article, that one of Professor Basun's slide, authors work with an Erdős-Rényi dense case. Instead, we are working with an exponential random graph. What is the exponential random graph? Is a random graph model, if you want, that is shaped through a vector of parameter. And it is called exponential because we can define the probability to have a graph, a specific graph with n vertices like this. So there is this parameter that in some sense regulates the number of edges. And then there is this parameter beta q that regulates how many triangles we... Yes, sorry?
Is m the number of vertices?
N?
The letter m.
The letter, sorry. Sorry, I write not so clear, is n. This is n.
So, no, the number of vertices?
Vertices, yes. And it's fixed, but we can think to make it grow. So let's, for example, take a perfect example. If beta 2 is greater than 0 and very, very big, we want the model to favor the presence of triangles. Instead, on the opposite side, if beta 2 is smaller than 0, maybe very big, smaller, we expect the model does not favor the presence of triangles. So I want to comment the role of this. In particular, you know that in the Erdős-Rényi, the presence of an edge is independent of the presence of another edge. In this model, some dependencies enter. And why? Because we have this. So this term will be, in some sense, involving. And it represents the most difficult part, because if there is not, maybe this is exactly a pure Erdős-Rényi in some sense. So we are making the model richer by introducing exactly this part. And obviously, to define a well-defined probability, we also need a normalizing constant that is this, and that depends on the parameter Q. So in order to find something similar to the Erdős-Rényi case, we want to make this exponential random graph near the Erdős-Rényi case. And how we can do it? There is an answer, and the answer is this. We have to pick beta 2 greater than 0. And why? Because in this article of Chatterjee and Diaconis, there is these sentences that gives a good idea. We expect, in particular, if we pick beta 2 greater than 0, that the exponential random graph is very near the Erdős-Rényi and U star, where this U star is a maximizer of a rate function. Let's suppose that it is unique for simplicity, okay? And what does to be indistinguishable means? It means that they both have the same limit as graphene, for example. So if we work with the cat distance, okay, we find that the exponential random graph converges to the graphene that is exactly the limit of the dense Erdős-Rényi. So when n grows, if we see to the graphene, we can distinguish the two limits. So in this sense, we want to work with these things in order to try to say that the things in our model does not change a lot from the standard situation, okay? And in particular, obviously, this hypothesis obviously helps. And why? In the article of Chatterjee and Diaconis, there is this very interesting picture that represents the value of U star depending on a pair of beta 1 and beta 2. You say that beta 2 is bigger than 0 to have this sort of convergence. And as you can see, for the same value of U star, that could be maybe different couples, different pairs of beta 1 and beta 2 that brings to the same U star. But there is a dangerous regime here. What happens there? Maybe there, if we pick beta 1 and beta 2 in this dangerous zone, their rate function does not admit a unique maximizer. This means that the graph, yes, is dense. It looks like Erdős-Rényi, but the parameter of the Erdős-Rényi is random, picked from the set of maximizer. So we expect that if we work with this set of pairs here, maybe it will be more involving. And so maybe we can think to work with the hypothesis that there exists a unique maximizer, maybe. Sorry? Here?
Beta 2 times
to the power of 3, sorry. It is the cube of u, sorry. Yes, this is a function of u and defined with the, yes, it is a power. Okay. And so, in particular, just have a brief recap of the initial condition. The graph is an exponential random graph where beta 1 is different from 0 and beta 2 is greater from 0. If we want to help ourselves, we can think that the maximizer U star is unique. Then we condition on this situation. and we called m, say, the number of edges. As I said before, the number of edges will be conserved because during the rewiring steps, we only move edges, okay? So we start introducing our set of labeled edges, and we also want to insert opinions. The opinions are presented independently, and they are distributed as a Bernoulli 1/2. This means that in the initial condition, in average, we expect the populations to be half red, half blue, for example, half 1, half 0, in average. Okay, so I do not know if I have enough time, so if you want, please stop me, okay? Let's see what we expect. I want to give before an idea, a sketch of an idea, and then I want to introduce maybe, if I have time, the mathematical results. So,
about 10 minutes.
10 minutes. Okay, just stop me if or if you have questions, please feel free to ask. Okay, so as I said before, we want to play with gamma. If gamma is exactly 0, we only have this case where we perform a rewiring. And if gamma is just too big, we are near a pure Bohr model behavior. So we expect that could be maybe the supercritical regime and supercritical regime where there are the yellow behavior that is near this and the red behavior that is near this. Let's try to understand what happens here. So if gamma is small enough, sufficiently near 0, we expect that the graph, the opinion of the vertices do not have a lot of time to change. And instead, the rewiring is very strong, and so the graph will separate into communities very, very fast. And so we expect that the model is quite rapid, a time of that is proportional to the square of n. And we expect the minority opinion to be conserved. So we expect that the minority opinion fraction is near the initial situation, that is 1/2. So we expect to find something near the initial situations, something like this. What happens in the opposite side? So when gamma is big, it is a regime where the Bohr model is predominant instead. And in these regimes, it's the opposite. The network does not have time to change very rapidly, but all the opinions are sufficiently changed, rapidly changes. And so we expect the process to last longer, and we expect the minority to be able to reduce. Okay, so maybe we will end something like this. So now we want, if I have time, to introduce the mathematical results. So it is exactly this idea. We want to introduce some stopping times. Let tau be the stopping times that represent the duration of our process. In particular, we also want to work with this that control the moment in which the minority opinion fraction reaches a threshold that we can control with epsilon. So this is defined to be the number of vertices that carry the minority opinion, that carry the minority opinion. And this is the fraction. At time 0, it is in average 1/2, and so we can control when it arrives to be pushed down. In particular, so if we fix this epsilon, there is a gamma 0 and maybe a gamma that depends on epsilon. Obviously, this parameter can depend on the parameter of the exponential random graphs too. And if gamma is small, we have that with high probability, the process lasts at most the square of n, and the minority opinion is conserved, as we said before, because for any eta that is arbitrary, we can bound by below the minority opinion fraction. On the opposite side, there is conjecture of gamma big. For every gamma bigger than this, we expect that before the time is finished, so before the process ends, we expect the minority to be reduced, okay, to arrive and be pushed down from these thresholds with high probability, of course. And this means that with high probability, we expect the process to last at least the cube of n. So it lasts longer, as we said before. These conjectures are exactly the theorems that are presented in the Basu and Slide article. So we do not expect any different from the classical behavior we're using at the Sreni case. And then there is conjecture number 2 that is very interesting and that answers the question, is the minority able to survive, okay, for every value of gamma that we can pick? So let gamma be your favorite value of gamma. In particular, there exists this epsilon such that when the process is finished, the minority opinion fraction is not 0, but is bounded below by something. So in a situation like this, we can never hand in the consensus. There is always the survival of the minority. And if you think to real application, I mean, this makes sense. It is quite common sense to understand and to think to a situation that represent these characteristics in which the minority, yes, can be reduced, but it survives. So these are our conjectures. So thank you for your attention. Yes, please.
So is it because the gap is evolving? Is it possible to majority become minority?
Yes, we define the minority to always be, yes, we do not say that the minority is 1 or 0. We always count the number of vertices that has the minority opinion, but obviously it can change. Yes.
And when you say absorbing state, it's like it's like consensus, right? Or is it different meaning for absorbing state?
I mean, absorbing state, always stated in a Markov chain that where we can't move. So if we arrive in that state, we can move anymore and the process will always happen like that. So there are possibly even different absorbing state. That means different ways the process can end.
Because if there are some nodes which are 0 and 1, and if these are connected, let's say, and then the two things can happen, as you've shown, is that either they should become like bipartite, like where only same nodes are connected, similar nodes are connected, or else everyone should become the same.
Yes, it could be.
One.
It could be also that possibility. The conjecture 2 says, okay, even if there is that possibility, we expect that with that probability there is the survival of the minority. But obviously, the state where all the opinion are the same is an absorbing state.
Like the expected number of connected components we could have by the end, like by the time we get to an absorbing state. Like the set of absorbing states would be characterized by like the set of like graphs that constitute connected components where in each connected component everybody has the same event, right? So basically, like, do we have any like idea of like what that limiting state would look like? Like on average, like how many like communities would we expect?
Honestly, this is a very good question. I honestly do not have any idea that is clear, but maybe, I don't know, there is someone that is working on that. And obviously, it is an interesting question to also understand how many communities do we have.
Give you a picture proof.
Sorry?
Give you a picture proof. Picture proof, I can tell you.
Picture proof?
In simulations, you know that.
Yes.
Use one column.
Oh, one.
Either side.
So
in simulations, you can see that at least when you simulated it a long time back, to his question, you get two communities completely connected and no interconnection between them.
okay.
That's what we get simulations. I'm not sure it's correct.
Okay. Sorry, can you repeat? I didn't. We, in the initial condition, in the initial conjecture, there was a conjecture that said, okay, there is a sharp transition. Maybe we are able only to say there is a subcritical and supercritical, but we expect to have a sharp transition. Yeah.
What happens in Basu's slide? What happens? The beta C is there?